Hi everyone. How is the conference so far? Enjoying it? Nice. My name is Nikita Nazarov, and today we will talk about debugging coroutines. By the way, I'm the Kotlin compiler engineer at Google. So first of all, coroutines are hard to debug, and there are many reasons for that. During my talk, I will break these reasons down and show you ways to overcome common issues when debugging coroutines. But in the beginning, let me show you the ultimate debugging tool, the print line. Raise your hand if you do print line debugging. There's so many of you. You're legends, guys. All right, never mind. So, first of all, why coroutines are hard to debug is that coroutines are asynchronous, which means they are not executed sequentially, unlike ordinary functions. Asynchronous code is generally harder to understand. It is even harder to debug. Moreover, it makes the debugger itself confused. Let me show you why on a small example. So we will be building an application that runs a couple of coroutines on a fixed thread pool. We start with the main function. Let's create a fixed thread pool of 3 threads and call it my pool. Then we do the run blocking call on our pool and call our coroutine main. Inside run blocking, we'll launch a coroutine that describes Kotlin. And we repeat it 6 times. In total, we have 6 coroutines running on 3 threads. Let's take a closer look at the describe function. It takes the identifier string as the parameter. It firstly fetches the description by this identifier. Then it enhances it. And then it returns it. So raise your hand if you think this code is hard to debug. Well, actually, not so many of you. I will try to prove you wrong. So let's run the debugger and try stepping through the describe function line by line to inspect the values of the variables. So we have put the breakpoint on the first line of the describe function. You can see that in the bottom of the slide, there is the variables view panel, where the debugger shows you local variables that are currently visible on a current breakpoint. Right now, there is only the identifier variable, which equals Kotlin, but we would also like to inspect other variables. So let's disable this breakpoint at first, because since we're debugging in a multi-threaded environment, this breakpoint may significantly spoil our debugging experience. And then let's try simply stepping over line by line. So we press step over, and it looks like the debugger disconnected. So it just quit. And I remind you that right now we only have 6 coroutines running on 3 threads. Imagine debugging larger applications. But anyway, we're engineers and nothing can stop us. So let's try again. So yet again, we are on the first line of the describe function. But instead of just stepping, let's put a breakpoint on the second line. And let's resume the debugger and see what happens. So finally, we hit this breakpoint, but variables in the view say, oops, wrong coroutine. So I think the debugger is trying to tell us something. Well, it actually could have happened that on the previous breakpoint, we were on one thread, but when we resumed the debugger, we are now on another one. So is there any way to understand which thread are we currently on? Of course there is. You can evaluate this expression. It says thread.currentThread.name, and it will return the name of the current thread that you have stopped on. Let's add this expression to watches. You see, the name of the current thread is mypool-2. But as far as I remember, we also have 6 coroutines in our application. So how do I get the name of a current coroutine? And to properly answer this question, I will have to tell you a little bit about the capabilities of the Kotlin X coroutine library. Well, first of all, Kotlin X coroutines has a debug mode. When the debug mode is enabled, each coroutine is assigned a unique name. It can be enabled with the -EA flag, or if you don't assertions enabled in your VM, you can enable it with this flag on the slide. So for example, if you are using Gradle with the application plugin, you can enable it like this. Or like this if you don't want the assertions. All right, so let's try debugging again, but with this flag enabled. And this time, we will keep an eye on the name of the current coroutine. All right, so we are on the first line of the describe function. We can see that the name of the current thread is mypool-2 at main-2, where main-2 is the name of the current coroutine. So let's resume the debug and see what happens. So now we are on the second line, and the name of the thread is mypool-2 at main-6. So it looks like after the resumption, we have changed the coroutine, and that's why variables in the view say, oh, oops, wrong coroutine. That is actually very upsetting, because how do we even debug this code? We tried stepping over line by line, the debugger dies. We tried putting breakpoints, and when we resume the debugger, we wake up in a different world. The only good thing that we know is the name of the coroutine of interest, and we can use it to our advantage. If you right-click on a breakpoint, you will be able to modify its behavior inside this window. So what is very important to us, you can add a condition under which the breakpoint will be triggered. So let's try adding the condition that captures the name of the coroutine of interest. So this condition is thread current thread.name.contains main-2, where instead of main-2, you can put any name of a coroutine that you want. So once we have done that, let's put this conditional breakpoints on every single line in the describe function. Let's run the debugger again. So yet again, we're on the first line, and the name of the current thread is mypool-2 at main-2. Yes, so main-2 is the coroutine that we wanted to capture, and we capture it. So it's nice. If we resume the debugger, we can see that the name of the thread is mypool-1 at main-2. So the coroutine switched threads, but we still managed to capture it. Also, values in the variables view say is the best. So that's progress. Resuming the debugger again, the name of the current thread is mypool-3 at main-2. So the coroutine has switched the thread one more time, but we still managed to capture it. So, and the variables in the view say is the best programming language in the world. So finally, we have managed to step through this 3-line function in the debugger. But at this point, we have been debugging for so long that I already forgot which language is the best programming language in the world. So let's try inspecting the identifier variable. Uh-oh, it looks the identifier was optimized out. Raise your hand if you have seen this nasty expression in the debugger. All right, guys. So why would the compiler want to optimize one single variable in our application? The debug process is already very hard, and now they tell us that we can't inspect variables when we want. And the answer to this question brings us to another reason why coroutines are hard to debug. And that is, suspend functions are not ordinary functions. The suspend modifier tells the compiler that the function can sleep and wake up multiple times, and the compiler has to implement it somehow. Let's try to understand how. So taking a look at the signature of the describe function, did you know that for every suspend function in your application, the compiler adds a hidden parameter called continuation? Continuation represents an execution flow that was suspended. It allows to resume the execution by invoking resume. And it is used as a storage of local variables values, what is very important to us. But there is more to it. So the compiler wants the suspend function to be executed multiple times when it wakes up. And to do this, it turns the function into a state machine. The idea is that when the function is resumed, different portions of the state machine are executed. To better understand this concept, Let's put labels firstly on the start of the function and after each suspension point. So we have label 0 on the start of the function, label 1 after the suspending fetch description function, and label 2 after the suspending enhance description function. So the compiler turns the function into a state machine. It looks like a when statement. Depending on the state machine label, different portions of the function are executed. In the end of each block, the label is incremented, so that when the function awakens, another block of the when statement is executed. And what is also important, local variables are captured inside the continuation. Also, the compiler performs the liveness analysis and nullifies variables that are not used in another blocks. But why does it do it? The answer is very simple, memory leaks. Imagine if your coroutine referenced a variable that retained 1 terabyte of data and then went to sleep forever. So that does not sound good. But is there any way to prevent the compiler from optimizing the variables? Of course there is. We can just print them out. Well, since variables are passed to the println function, the compiler will not optimize them. But what if I don't want to print every single variable in my application to be able to debug it? There is an answer. The Kotlin compiler team created a flag that is called -Xdebug. So this compiler flag prevents specifically this optimization. So when this flag is enabled, the compiler will no longer nullify variables that were supposed to be nullified. So how can you add it? For example, if you are using Gradle with the Kotlin plugin, you can do it like this. Kotlin, compiler options, free compiler args, add -Xdebug. And please don't use this flag in release builds because it might cause memory leaks that will be extremely hard to find. All right, so running the debug again, but with the Xdebug flag enabled. And you can see that the identifier variable is optimized no more. And now it is clear that Kotlin is the best programming language in the world. So finally, we managed to debug this 3-line function. I guess you guys who didn't believe that this is hard to debug were proven wrong at this point. So we spent so much effort. But anyway, let's move to another reason why coroutines are hard to debug. And that is coroutine stack traces are cryptic. What it means is that since coroutines are asynchronous, their stack traces usually never represent how functions were actually called in the source code. But there are tools for that. And the tool is called stack trace recovery. And let me show you how it works on a small example. So we will be building an application that loads 2 images by their names and then combines them. So we have a window class. Let's create a dedicated scope for our window to run coroutines on. We have the display images functions that accepts names as arguments. And inside this function launches a coroutine that loads and combines these images. The load and combine function is a utility function. It creates a dedicated coroutine scope, and inside it asynchronously loads 2 images and then just combines them. So it's very simple. But what happens if the load image function throws an exception? Let's take a look at it. So what we have here, loading JPEG image failed, and we have some information about the load image function and also load and combine. But window is not mentioned, and it's very unpleasant because imagine if load and combine function is a utility function that is used by many classes in your application. And it means that when seeing such an exception, you effectively can't understand what is the root cause of it. And that's where stack trace recovery comes in handy. As I already mentioned, Kotlin X Coroutines library has a debug mode. The debug mode not only adds unique names for every coroutine, but also enables stack trace recovery. Stack trace recovery is a mechanism that tries to to extend the exception stack trace by combining it with the stack trace of a place where the exception was asynchronously caught or thrown. It can be enabled with the options on the slide. So taking a look at our application again, we have a window class with the display images function that launches a coroutine, and we have a load and combine function that asynchronously loads two images and then combines them. And then the exception happens in the load image function. But now we have assertions enabled in our VM, which automatically enables stack trace recovery. Let's take a look at the stack trace. So now loading JPEG image failed, but now the exception was rethrown. And we can see that the original exception contains information about load image and load and combine functions, but doesn't mention window as previously. But the new exception not only contains information about these two functions, but what is important, it contains the information about window and about the display images function. So that's very good, but there is a catch. Let me show you what could go wrong on a very small example. So we have a function 1. It's very simple. It just sleeps and throws an exception. We have function 2 that calls function 1 and then sleeps. And we have function 3 that calls function 2 and then goes to sleep. The main function just calls function 3 inside the run blocking call. So the call graph of this small application looks like this. Main calls function 3, that calls function 2, that calls function 1. So it is very simple. So let's run this application with the -EA flag enabled and see how the exception looks like. So here it is. It says exception in fun1. We have some information about function 1 and the main function, but we absolutely have no information about function 2 and function 3. But we have stack trace recovery enabled, so it's not that easy. Taking a step back, let's try wrapping function 1 in a coroutine scope, and then take a look at the exception again. So we have function 1, and now the exception was rethrown, and we have all of the information that we need. So it looks like stack trace recovery only works properly if the exception thrown passes scope boundaries. But what if I don't want to wrap every exception throwing function in a coroutine scope? Or even worse, what if I'm using a library that uses Kotlin Coroutines and the library throws an exception and I can't understand its stack trace? Well, there is a tool for that. It's called stack trace decoutinator. Well, first of all, it's an open source library. It enhances coroutine stack traces. It's by loading a Java agent that replaces the implementation of coroutine awakening. It generates methods at runtime with names that match the entire coroutine call stack. And these methods call each other to mimic the real stack trace. So you can see that there's quite some runtime overhead for it. But you can still use it for the debugging purposes. How to enable it? For example, if you're using Gradle, you can add a dependency on this library. And then, inside your application, you will have to call this line of code to load the decoutinator agent. So let's take a look at the exception stack trace once more. So we have exception in function 1, some information about function 1. We have some frames that are coming from the decoutinator because it replaces the coroutine awakening methods, so we see it in the stack trace. And we have the information about function 2, function 3, and main. And we even didn't have stack trace recovery enabled. So is it useful? I guess yes, maybe not at runtime, but for debugging purposes, sure. And we just added one line of code to our application. So ultimately, it's for you to decide when and how to use this tool. So moving on to another reason why coroutines are hard to debug, it is that coroutines are many. There can be many coroutines in your application. Unlike threads, coroutines are lightweight, and you can spawn them here and there, and boom, there are 1,000 coroutines in your application. But it comes with a cost. It may be very hard to inspect the state of such an application, and also it's very hard to try to understand which coroutine is doing what at a fixed point in time. But there are tools for that. I will show you how these tools works on our previous example. So we have the window class, we have the load and combine function, and we put a breakpoint on the line where two images are combined. In the debugger, you will be able to open the Coroutine panel. It does a couple of things. First of all, it gathers information about all of the coroutines in your application, their states and stack traces. And also, it groups these coroutines by jobs or by dispatches. Let's take a look at the dispatches grouping first. So we can see that all of the coroutines in our application are under the default dispatcher, but when debugging larger applications, you will see other dispatches as well. Clicking on the dispatcher, you will see a list of running coroutines. And when you click on one, you will be able to inspect its stack trace. And we can see that this coroutine runs load and combine function. The second and third coroutines run load image functions. If we take a step back and take a look at the jobs grouping, we click on the jobs and we see the supervisor job. If we take a look at the source code, indeed, the scope that we created for our window is a supervisor job. So if we click on the supervisor job, we will see standalone coroutine. The standalone coroutine is the one that was created by the launch call inside display images. If we unwrap the standalone coroutine, we can see the scope coroutine, and it is the one that was created by the coroutine scope call inside load and combine. If we inspect the stack trace of another coroutine, we can see that it runs the load and combine function. If we click on the scope coroutine, we would be able to see two deferred coroutines. And these are the ones that were created by the async method call inside load and combine. And we can see that these coroutines run load image functions. But there is another important capability of the Coroutine panel. If you right-click on it, you will be able to capture coroutines dump. If you click on this button, you will see a window with a list of coroutines and their stack traces. But what is important, you will be able, by clicking this button in the red box, to export this dump into a text file, and then you will be able to use command line tooling like grep to find the needed information. Another tool that does a similar thing but a little bit differently is the Coroutines text plugin for Intellij IDEA. Well, first of all, it is an open source project. It can be downloaded from Intellij plugin marketplace. It creates a view with the graph representation of coroutine stack traces. Similarly to how it is done in parallel stacks of JetBrains Rider or Microsoft Visual Studio IDEs. So in our window application, we'd put a breakpoint on a line where two images are combined. Then you will be able to open the coroutine stacks window. It looks something like this. It's a little bit overwhelming at first, but let me try to explain how it works. So first of all, we have boxes inside this panel. These boxes contain stack frames. These boxes also form a tree. On the top of each box, you will be able to see how many coroutines are either running or suspended, and how many of them share this exact stack trace. So in the root of the tree come common frames for all coroutines in your application. And leaves of this tree represent unique frames for your application. Then, if we click on the minus button, we'll be able to zoom out to get a vector picture of the graph. And we can also navigate this panel with a mouse cursor. If we click the 1:1 button, we can get back to original zooming. And also, a very nice thing is that the coroutine that we put a breakpoint in, its stack trace is highlighted with the blue color. So here is it on the slide. The yellow frames are frames that come from libraries, and you can filter them out by pressing the filter button. And we can see that for our application, at this particular point in time, our coroutines have no frames in common except for library frames. But let's get back. There is a photo button that captures a coroutine dump, exactly how it is done in the Coroutine panel. And there is a special button to add creation stack frames to the window. Creation stack frames are stack frames that represent the place where the coroutine was created. So if we press this button, creation stack frames are highlighted in blue. Let's try to zoom in and inspect the panel. And we can see that the load and combine function, the coroutine that runs load and combine, was created inside the display images function. And the coroutine that runs load image was created inside load and combine. So finally, let's revise what we have learned today. So first of all, we learned how to use conditional breakpoints to ensure that we are inside the same coroutine when we are debugging. We now know how to use the coroutine debug mode to enable coroutine naming and stack trace recovery. We also learned how to use the Coroutine panel to inspect the state and hierarchy of coroutines in our application. And now we know that the Kotlin community tries hard to improve the coroutine debugging experience, so make sure to check out the Coroutine stacks plugin and the stack trace decourutinator library. And what is most important, debugging coroutines is hard, but not because it is a bad feature, but because it's a very powerful one. So enjoy it. Thank you for your attention. And now, question time.
Hi, folks, there is a mic standing there, so please line up there for your Q&A.
Sure. I was wondering if you see any possibility for recent JVMs with virtual threads which preserve stack traces even when they're split, and any chance of using that to simplify the stack traces of coroutines to a more readable form?
Well, I actually don't know. I think there was a talk on the previous Kotlin conf about combining the virtual threads and coroutines, but I don't think that adding virtual threads to a coroutine-based application will anyhow enhance the debugging experience. I think the debugger will somehow handle this case separately.
Yeah, two questions actually. The stack trace recovery, I think it also has some additional requirements on the exception, right? It has to be serializable or something like this. Do you know if this is still there?
No, I don't know, sorry.
Okay, because they're also not very great if you get exceptions from some library and then they're not serializable. It doesn't help you anything.
Yes, I don't know, but I guess you can look it up.
All right. Yeah, the documentation is also not so great. Second question, do you know, like, you have to enable this debug functionality for the stack trace recovery and so on. Do you have any experience how big the performance impact or so is?
The performance impact is negligible. So you can enable it with the assertions, but if you don't want the assertions, you can add a very simple flag. But the performance impact, yeah,
so this one
it's
you
very
can
low.
Leave on in production pretty much.
Hi, I had a question about the debug flags. So is that something that happens in compile time, or is that something that happens in the runtime injection?
Sorry, can you please repeat the question?
Yeah, so for the debug flags, my
Yes.
question was, does that happen at compile time?
Yes, so the Kotlin X coroutines debug mode is enabled at runtime, so you have to add flags to your VM. But the Xdebug flag is a compile time flag. You have to pass it to a compiler. So to actually prevent the compiler from nullifying variables in your application, you have to recompile your code and then debug it.
Okay, so then the follow-up is, if you have cross-module like debugging, you have to then enable that and recompile all of your other modules as well, right?
Yes, yes.
So if you're using libraries, you won't get stack traces for your libraries as well?
No, you will get stack trace because stack traces thing is enabled with the VM options. So for libraries, you will get stack traces, but yeah, you won't get the variables with the libraries.
Thank you.
Hi. How difficult will it be to make a debugger when you pick next to stop in the same coroutine?
Well, I guess I have shown this in my talk.
No, but can you do it automatically? Just do next, or?
Yes, so yeah, you are talking about extending the debugger functionality to be able to do it. Yes, it is doable, but the only issue is that imagine if you want to step over inside the debugger, but when you press the step over, your coroutine just slips forever, and then the debugger just hangs because of it. So it is doable, but there are some corner cases. So I think the Intellij Debugger team is working on that right now.
Thank you.
So all right, no more questions. Thank you very much for coming.